Hello, welcome to Maths with EJD. In this video, I want to show you the Python code for simple linear regression. First of all, I'll be using the same data like what I did in the last video, talking about how hours of study and exam score, how hours of study can predict exam score. We actually got a kind of perfect model in that previous case because this data is for the most part it is made up, as you can see. So, but I mean it's good for demonstrating the idea of simple linear regression. So in this case, you can see okay, to make me be able to refer to the lines, I just show the line numbers. So from lines 1 to 4, that's us importing the necessary libraries for this task. We have NumPy, that's numerical Python. For it's just like the name implies, it's for some numerical stuff like maybe calculating one thing or the other. Let me see an instance where NumPy is used. Anywhere you see NP, that's where NumPy is actually used. Let me see. I've not seen any. Maybe NumPy is not even necessary here then. So if you don't see NumPy in the body of the code, then it's not necessary. Okay. Yeah, NumPy is not used here, at least from what I see currently. But so that's okay. So we can do without the first library for NumPy. So we can do without it. So the next one is pandas. Pandas, NumPy is for numerical calculations, right? So pandas is for data analysis. So things like, defining a data frame, you see PD dot data frame. So without PD, you cannot do data frame. So that's one place. Then of course, defining your variables like that, you need to actually use. So this DF now is dependent on what you have declared before. And then I think there are a few other places like yeah, a few other places, especially that first line where you define data frame. That's where that is used. Then you also have StatsModel.api as stats model. So we are dealing with statistical stuff. And since linear regression is a statistical thing, right? So you need SM here, you need the stats model thing here to fit the regression model. That is line line 23 is where we're fitting the regression model. In line 20, right? Here we're adding a constant to the independent variables like that. Then so the fit is happening in 23. Then in 26, we need a model summary. So that summarizes, it gives us things like the p-value and all of those information that one may want to get. So let me go and then of course matplotlib is to represent, at the end of the day, you need to show the line of best fit or the regression line, right? So we need a data visualization package to get that happening. And that is why you have the fourth library, import matplotlib.pyplot as PLT. All the NPPD, SM, and PLT are known as aliases. So instead of having to write, imagine each time you need to write PD, you have to write pandas. Or imagine each time you need to write matplotlib.plt. So normally what you should be writing is matplotlib.pyplots. So everywhere here, in all these places where you see PLC, normally you should write matplotlib.pyplot, matplotlib.pyplot.scatter, matplotlib.pyplot.plot. But because you are giving it an alias, so you can as well just make your work easy. So in lines 7 to 9, so here we are declaring the data using what is known as a Python dictionary. So they're using a dictionary here. And for a dictionary, right, it's a key value pair. So here we are looking at, we have two key value pairs. Hours of study is a key, and the values are 1 to 8, and the exam score is another key, and the values are 55 to 90. And then having use that dictionary, we can now, line 13 now, we are converting that dictionary into a data frame. So here, and data frame can actually store multi-dimensional data like that, like what you have in Microsoft Excel. It stores these things in rows and columns, so such that column 1, of course, Python calls that 0. So counting in Python starts from 0. So column 1 here will be hours studied, and you have 1, 2, 3, 4, 5, 6, 7, 8. And column 2, which is column 1 in Python, will have 55 to 6 to 90, just like we had it when I was teaching, when I was doing the calculation manually. So like that. So in 13, like I said, oh yeah, that's what 13 does, right? in line 16 and 17, we are now saying, oh, let the first column be our study. So that's our X. So we say X, DF, our study. That means from this data frame, DF now, where the our studied column is actually assigned X and the exam score column is assigned Y. And then in 20, we are adding a constant to the independent variable. Add a constant to the independent variable X. That's probably where the intercept will be coming into the show or something like that. So we have that. And then line 23 fits the regression model. So this is where the actual regression thing is happening. So we have model equals SM, and that's where we used StatsModel.api. So, and we have a method called OLS. I think it should be ordinary linear least square or something like that. That's where, so we can only get that from SM. And then the fit helps us to fit Y to X. So it fits. So all the maths I was solving, this one line is just taking care of that right there. Then line 26 displays the summary of the regression result. That where you see things like the values of the coefficients, the API, the p-value, and things like that. They are all in the model summary. Then you have line 29 and 30. So here, so we are just extracting coefficients. So you want to extract the intercept. That is model.params 0. That's the first thing. Then the slope, model.params 1. That gives you the value of the slope. Of course, remember the intercept from what we got the other time was, I think that was 50, while the slope was 5, if you remember. So since we're using the same data, we should get the same thing here if everything works well. Then, of course, if you use some other kind of data, right, your answers might be slightly different because computing it may be more efficient than solving it manually. So you may get better results here than there. But from what we did already, we're getting perfect value. So we should expect exactly the same thing right here. So if you also want to see your regression equation, you can have that. So here, line 33 is showing us the regression equation where we say exam score equals intercept, we want it to be in 4 decimal places, slope also in 4 decimal places. So that's whatever we get as intercept, which we have extracted from 29, will come here, and the slope will also come here, all in 4 decimal places, times hours studied. And then lines 36 to 40 is where we are plotting. So we say we do a scatter plot. So we have hours studied and exam score. That is the original thing from your data points. That's where you're plotting 1 against 55, 2 against 60, 3 against 65, and up to 8 against 90. That's what line 36 is doing. That's the scatter plot for the raw data, or what you can call the observed data. In line 37, that is where the fit is coming in. So you have hours studied. In fact, you also have the model predict. You want to model predict X, and then so you now get your regression line. So that line now that you get from your calculation, like that, Y equals 50 plus 5X. So this is going to be plotted using line 37. And then, of course, you have the title, that's our studied versus exam scores. And you have the X label, that's our studied. And then Y label is exam score. That's you labeling the graph now. And then in line 42, here you are just displaying the regression equation on the plot. So you want to show the line on the plot now. So that the regression equation which you have from 33, you just want to have it showing on the plot. And this 280 is for you to move it up and down. I might be able to show that when we go on. And of course, legend, grid, and all that. So legend is if you have more than one kind of thing. So this legend is what's going to help you say this is X, this is Y, and things like that. And then if you want grid, you say true. If you don't want grid, you remove the true. Then, so line 50 to 52 is where we are making prediction to say if somebody studied for 5 hours, so what will be the predicted? So the predicted score now will be intercept plus the slope times hours studied, and then to now give us the predicted exam score for the 5 hours studied, something like that. So if you run this now in one blow, all that thing we did in 5 or 10 minutes can just happen in less than 30 seconds. So just click on that and just give it a bit of time, and then that jumps out at you. So this is what you have, right? So this is hours studied versus exam. So you have the scores 55 to 90. These are the hours studied. So the blue lines now is where you did the data points. Like that's where you did the scatter plot. And then you can see the equation exam score equals, okay, before we go to all those places, right? Yeah, from the table, you can extract these values. You can see that the constant coefficient, which is actually the intercept, is 50, and the coefficient of our studied, which is our B1, is 5.0. So these are the standard errors attached to all of that. Then you have the p-values too, which are actually significant. So all that go on like that. So if you need things like R squared shows it's perfect. Adjusted R squared to shows it's perfect. So if you need F statistic, all of those things will just come up like right here. Even the AIC, Akaike criterion or something like that, you know. So degree of freedom, residuals, blah blah blah. If you need all this extra information, but the key thing to get the equation will be the constant coefficient, which is the intercept, and then of course the slope, which is the coefficient of the independent variable, which is our studied here. And if you need all these other things, omnibus, blah blah blah, you can get them. That's a summary. Then here, standard errors assume that the covariance matrix of the errors is correctly specified. So you see, it's just like what we did. And for the prediction, right, predicted exam score for 5 hours study is 75, which matches. So you see, 1, 2, 3, 4, 5, then 1, 2, 3, 4, 5. So 55 and 75, they match them. So just like what we did when I was doing it manually. Okay, before I end this, I just want to do something on the fly, so to speak. Um, so I want to fit regression. I want to do a regression of uh what somebody based on somebody's performance in maths, what would they score in physics? I want to do that. So let's say this is mathematics, and this is physics. So we can actually fit a model to, if you know the physics scores of a number of students and their math scores, we can actually make a regression line to say, okay, if this person scores this thing, okay, like here for instance, now we did for 5 hours, right? What if somebody studies for 10 hours? Of course, probably the person is going to get more than 100 over 100, right? Okay. So you see, if you study for 10 hours, you get 100 over 100, something like that. So, you know, all that can happen like that. But then now I'm going to talk about maths and physics. So if you get certain scores in maths, what what are the predictors? How do your math scores predict your physics scores? That's the idea. So let me say, we have for math scores we have 45, we have 65, we have 32, we have 78, we have 34, we have 47, we have 91. So they have to match, right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Let's say again we have 77, we have 61, we have let me do 10, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, one to go. Let's say this person now has 23, and then for physics, we need it to be 10. This one is too predictable. I just want to switch things up. Let's say, okay, this person gets 90, and then we have 57, and this is, say, 40. This is, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's say this one is 60. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. Let's say this is say 64, like that. So we have 10 scores. So someone gets 45 in maths and then 90 in physics, then 65 in maths, 57 in physics, 32 in maths, 40 in physics, and so on and so forth. So we just want to see, based on this score now, of course, it's made up clearly. In reality, you may get something else, but this just to explain how this goes. So our X values will just be mathematics. So we want to use mathematics as predictors for physics, mathematics, and then exam score here becomes physics. So we just want to use the same variables. And then where else do we have to change stuff? Here now, we want to know what physics will look like depending on maths, okay? So our studied here becomes mathematics, like that, mathematics. Statistics. Okay. And then here again, this is mathematics. This is physics. Then our studied again is our studied would be mathematics, right? That's like our independent variable. Well, physics is the dependent variable. So here we just say uh mathematics versus physics. Mathematics, mathematics versus physics, physics scores. And then first this will be mathematics, and this will be physics. Then I think we are good. Okay, I guess there's one more thing down here. So predicted exam score. So we can now say predicted physics score. Predicted physics score. So let's assume that somebody now gets, did anybody get 55 in maths? Good. Nobody got 55 in maths. So what if somebody gets 55 in maths, what is the person's predicted physics score going to be? So exactly the same thing here, but now we have 10 data points. So you just run it, and in 30, yeah, this is even too very fast. Now you can see the thing is that equation is shooting up because the graph is different now. So we can actually use this numbering to adjust it. So let's see. Um, so we have it's 20 to 90, 20 to 40 to 90, like that. So um let's do like 50-50 so that it will be centralized or something close. Let's see. So that helps to adjust. So okay, this is even too much. Okay. So for the x-axis, the middle is like 45. So let's do 45, 45 and see what happens. Okay, no, that should be like x-axis is like 50. Let's do 45, 45 and just see 45, 45. Where's that now? 45, 45. That may still be somehow, but let's see. Okay. For the y-axis, we have to move it to like, let's move it to like 65. X 65. So it can go up. Oh, okay. X is X Y should be 65. So let's say what is that now? So this should be like 65, the Y axis. The X can be like 35. Let's say. Okay, this should be better. Yeah, something like this. So we can make it even better. So it means physics is equal to 56.2088 plus 0.2241. So that means that even if the person, without doing maths, even if you don't have anything about maths, the person already has physics 56.2088 in physics. But for every 1 mark the person scores in mathematics, uh, so the physics score will be boosted by an additional 0.2241 marks, like that. And if you so for anybody who gets 55 in mathematics, they're most likely going to score 68.53 in physics, you know. So 55, let's say where 55 should be. Okay, this is not arranged orderly. So this is more like the kind of thing you'll be coming across most of the times. So, so that's how that goes. So you can use it for so many scenarios and go on with. So you can see that the intercept is the 56.2088, while the slope is 0.2241. So that means physics is equal to 56.2088 times 0.2241 times mathematics, like that. Then of course you can see the R squared and R squared and adjusted R squared. They're not looking as pretty as what we had before, where it was actually a perfect one. So, so it mean in a way too, you can say that maths, your math score is not a very good predictor for physics based on this data. Based on this data, So the particular data you're using matters. And don't forget, I just made it up. The scenario can be different depending on the kind of students you have and all that. So all of these things actually go on. So thank you so much for listening this much. You can play around with this code, just modify, import data. So you can have very large data. That's why coding becomes important. Imagine you're doing this for like 1,000 students. So having to do it manually is just totally out of it. So it's better to use coding. And if you have not subscribed to this channel, do that right now. Thank you. And of course, hit the notification bell so you can always get alerted when a new video is released. Don't forget to comment. Comment. Let me know if you want me to teach a topic or solve a problem. And of course, like and share so that more people can get to learn all these things. See you again. Bye.